So today's topic is virtualization and containerization. Overview of virtualization and containerization. Now, let's learn about what this virtualization and containerization is, right? So virtualization and containerization are techniques used to create isolated environments for running software application. They enable better resource utilization, scalability, management of software system. Okay, so what exactly are these two? This is to just make sure that, um, see, for example, running Python. I was talking, right. You need Python binaries and Python, environment, like Python related software installed. And to run Node.js, you need Node.js and Node.js related binaries to be installed. Similar way, if you want to run Go, then you need Go application. Now think about that. In a single machine, you are running so many stuff. Like say for example, my local machine. I have installed Python. I have installed Go and all that. It's not just making my machine heavy. There are many chances then each of these application might run on different ports. Suppose I'm running one application for say Python in port 80. I want to start another application in port 80 using Node.js. I cannot do that because single host can only one port is allowed. For the same one main port is allowed. Okay, but with virtualization, I can actually run Python on say different port. I mean same port virtually, and I can run same, for example, Node.js or any other programming language on different port. Okay, so we'll come to all that anyway. While going through this all these courses and all, we'll go through every single stuff that we're going to talk about. Now, just as a revision, like what was virtualization, what was the containerization, we'll just go through it and then we'll explore the next topic. Okay, let's minimize this one. Okay, so virtualization. Virtualization is a process of creating a virtual, creating a virtual representation of physical resource such as server, storage, or network. It allows multiple operating system OS to run on a single physical hardware system simultaneously. Virtualization relies on a hypervisor. What is hypervisor? A software layer that manages allocating resources between different virtual machines. So, in simple sense, just to remind you guys that what was the virtualization? Virtualization was running multiple OS, okay, in a single host or any. Suppose you have your own MacBook or Linux. On top of that, you want to run maybe one or two more like OS, maybe Windows or maybe Linux inside your existing machine. That's the way of achieving this called virtualization. Okay, and there is of course to achieve this virtualization, there are many softwares available, which ideally call hypervisor. And there is two kind of hypervisor. One is a bare type 1, we call it bare metal hypervisor, and type 2, which is the hosted hypervisor. Now, what is the bare metal hypervisor? So this type of hypervisor run directly on physical hardware, providing the best performance and resource management. So usually, like you have your OS, and on that this software is installed. There is no other software in between. But for the hosted one, suppose you have your MacBook or your say local machine, and then on top of that you have another software, and that software have this virtualization. Then it's called hosted. Okay, like it's not directly that hypervisor is not installed in the OS. Instead, a software managing this hypervisor then is hosted. If there is no software in between, like the hypervisor itself managing the OS resources, then it's the bare metal. Okay, and in the interview question, suppose they ask what you should use, if you want to use a bare metal or you want to host it, then you have to ask like what is the application overhead, or what are the resources, like do you want the application to be robust, like more of these things, like things, say resource utilization, say provisioning, the RAM or CPU, all you want to manage in this main application, that's fine, bare metal. If you don't have that, you want a more advanced control, like exactly how much resources should be allowed to a particular application, those kind of requirement, like fine tuning the resource allocation, then it's better to go for the hosted solution. Okay, so what is containerization? A containerization is a lightweight form of virtualization. So again, it's a virtualization but a bit more lightweight. Okay, that involves packaging an application and its dependencies into a single portable unit called a container. Okay. And then containers share the same OS kernel with the other containers on the same host, which makes them faster, more efficient to compare to traditional virtual machines. And let's complete this entire para. So containers are isolated from each other, ensuring consistent behavior across different environment. Containers rely on container runtimes such as Docker, Containerisation, CRI-O for managing lifecycle. Then container orchestration platform, already Kubernetes, Docker, Swarm, Amazon ECS, which help us to deploy and all that. Now, if someone asks you what is containerization, you can say it's a form of virtualization. Now you already know what is virtualization, right? It's creating virtual, operating system, virtual, storage, virtual networking, all that stuff, right? So containerization also, for each container, you also have its own OS, its own storage, its own networking, right? Now then, what is the difference? See, you have to run container inside a virtual machine. You cannot, in the real sense, you cannot just directly run a container. To run container, there has to be a run inside a host. Host can be normal host, like a physical host, or it can be virtual host. So it's a virtualization inside virtualization. So you have virtual machine, suppose Ubuntu or maybe Windows, and in that virtual machine, you can have containers, and that containers can have Ubuntu, can have Windows, can have any other OS. That is a call containerization. Now, containerization, why we are saying it's not a, why then we're not saying it's a virtual machine? No, it's not a virtual machine, because virtual machines have the capability to interact with the hardware. But these containerizations, okay, doesn't have the capability to directly work with the kernel or work with the hardwares. It has to go through the host operating system or virtual machine running. So virtual machines host is has to go through. That's why we're calling container. So container in the sense, we have for a container, say box. In box, we have put OS, we have put all the application dependencies. For example, to run Python, we need Python binaries. Suppose, for example, for running Node.js, you need Node.js binaries. To run Java, you need Java binaries, right? So in that container, we have put operating system. On top of operating system, we are putting, say, this Python software or any other software, right? And then we are copying our codes. So we have Python codes. We are copying our codes to that particular container. And then at the end, we are saying how you can run this container, right? We are mentioning all that into the single containerization or single containerization method or image. We are mentioning all that, okay? Now, in this containerization, you have like what we are achieving by doing this containerization, right? Suppose you run a normal program. So your virtual machine have 4-core CPU, okay, or 4 CPU, and it has 18 GB or say 20 GB or some very high amount of, for example, RAM, right? So if you have a single application, okay, then that single application may use single core, dual core, is not like capable of utilizing all the CPU cores, right? So what happening there? There is a resource wastage, right? And in order to not like avoid this resource wastage, why not? Suppose we have 4 CPUs, so we can run copy of our application, like 4 copy of our application that running on single core. What will happen? We are here utilizing our CPUs 100, like we are using all the cores. So there is no resource getting wasted, right? So this is one of the very important reason we have this containerization. And of course, there are more, like suppose you make one image or one container, and it will run consistently exactly same way for any host you run, if that support that running that particular container application. So this is the, I would say, main benefit of this containerization. Again, containerization is a kind of virtualization, but that happens inside another virtual machine or maybe normal machine. So that is the containerization concept. Now, what are the key differences between this virtualization and containerization? First is this resource utilization. I mean, I was saying that same stuff from the past few minutes, right? So So in containerization, like what are the key difference between virtualization and containerization? First is resource utilization. I mean, last few minutes I was talking, right? So containers are more lightweight and have a smaller footprint, like smaller size, and they share same OS kernel. As I was saying, it's a virtual OS or it's maybe normal OS, a normal machine. It's running inside that OS, and it can run multiple copies of same containers, right? To work to distribute the workload, and it can share like same resources with other VMs, or not, I will say in a single VM you can share resources in multiple containers, right? So it's achieving virtualization inside a virtual machine. That kind of course, in a virtual machine also you can run another virtual machines like normal virtual machine, but that would be too heavy, and it will break your like normal virtual machine as well as the new virtual machine that you're going to run. Just very risky to have, or say is it very not so performance if you run virtual machine inside a virtual machine. But it's okay, or it's even better to run smaller virtual machine, like some form of smaller virtual machine which can run on virtual machine, like this container. It's a form of smaller virtualized machine or small virtual machines which can run inside bigger virtual machines. That will be very, of course, full resource relation uh, and better performance. Okay. Then the startup time. So, even if it's a virtual machine, then, to booting up, it takes a lot of time. Suppose you have your normal machine. There also, if you shut down the machine and then start up, it takes some boot time, it takes some time to load things up, right? So it's time consuming. But for containers, you don't need that one. It's lightweight, right? So like you start a container within fraction of, I think, milliseconds, it will start if the application is not too heavy. So startup time is very, very less for the containers. I'm not talking about the virtual machines, like normal virtual machines. Normal virtual machines can take too much time for load up. Maybe you have installed so many software, so many startup programs, right? Then it may take time. But for containers, which is a small form of encapsulation, a small form of virtual machine, will not have that much of workload, right? Or not have this kind of complicated thing installed and running. It's just purposely built to run one particular application. It will not have all this complicated software. So it will be faster to load. Then management. See, virtual machines are managed by hypervisor. By now, you already know that, right? But for containers are managed by the container runtime, like Docker, say Kubernetes, Docker Swarm, for example, Amazon ECS, or maybe other softwares, right? So it's their overhead, not our overhead. We don't need a software to manage that, but there are many softwares which you can use to manage these containers. Okay, then like let's come to the management part. See, VMs. Suppose we get a VM from AWS or Azure or GCP. We are, of course, managing the machines to be patching, but how that machine getting provisioned, how they're managing the physical architecture, we are not taking care of that. We don't worry about that, right? It's the managing hypervisor is actually the worry of the cloud service provider, not ours. But how we manage containers, how we manage the application inside containers, that's our headache, because we are the owner of this, software that is getting deployed and running, and we have to use available software, Kubernetes, Docker Swarm, all this application to run the application and to manage the application, like running is a container, right? So that's our problem. So VMs, cloud problem, right? And containers, our problem. Then portability. Now, container package application, you guys now by know that it container already have its OS. Container already have its dependent softwares, or say dependent packages and codes. So it already is a smaller package which have everything that we need to run application, right? But for the virtual machine, it's kind of, even though you can create images, it still doesn't, like, not every suppose, for example, I will give you a very quick example. Suppose you have Amazon EC2, right? That's a virtual machine. Can you run, like, can you get an image out of this Amazon virtual machine and run on, say, GCP or run on Azure? No, you cannot do that. There is no such thing. They cannot support one virtual machine of other cloud service provider in another cloud service provider. That is never supported. Okay. You can export application, you can export database, you can run it there, but not the entire OS, like entire AMI or say machine image, you cannot run on other cloud, right? There is limitation, isn't it? But containers are independent, right? So containers, we can install all the softwares. Container we install, it's already have its own OS, it's already have all the dependencies installed, and it's portable. So if you created one container image, you can share it anywhere with any cloud platform, with any individual user. I think one of the many important stuff that suppose you are running EC2 like AMI, right? So AMI you can run on the cloud, say maybe AWS cloud, maybe GCP cloud, their own AMIs you can run. But so not AMI, the machine image, okay? But you cannot pull that machine image to your local system. You cannot run that, right? You have limitations. You cannot do it. But for container, you can easily achieve that. For container, you can package application and run anywhere where this container platform supports. Okay. Then I mean that covers the portability part. Okay. So both virtualization and containerization offer unique advantages. Organization may choose to adopt one or both. Like usual cases, if you use only virtualization, okay, it's virtualization. You may not need Docker. You don't have a Docker requirement. But if you have a Docker requirement, you are bound to run a Docker application inside a virtual machine, right? So behind the scene, you're using virtualization or say the virtual machines, right, for running containers. But that not might be the case for the virtualization. So virtual machines help run the these containers, but containers run on this virtual machine. That's the relationship you should understand. Okay. Any doubt on this last? I mean, anyway, we'll go through all that. Any doubt you can raise hands. Now, virtualization benefits, I think we already ran over so many benefits. I'll just quickly go through. So virtualization allow multiple virtual machines to run a single physical server, which leads to better utilization of CPU and memory and storage, right? And then cost savings. Just give me a moment. By consolidating multiple workload on a single server, organization can reduce their hardware, power, and cooling cost, isolation, and security. So each virtual machine run a separate environment isolated from other VMs, which help its preventing potential security breaches and maintain application stability. I will just say some words on this part. Suppose I am running a EC2 instance in AWS, okay? Which is a virtual machine, right? And somehow my machine got hacked. Is my machine got hacked means all the other people running on AWS machine got hacked? No. That's because why? It's a virtual OS. It's have limitations. It cannot interact with other isolated virtual machines. So they are secure. It's only my machine gone bad. So I have to think about how I can improve all that, right? So that's one of the security feature you can get by utilizing virtual machines. And you should use virtual machine, by the way. Then easy maintenance and management. Okay. So virtual machine can be easily migrated, backed up, restored, and making so in that way, making maintenance tasks straightforward and easy, right? Then simplified testing and development. So developers can quickly create and manage multiple isolated environments, for example, testing, staging, pre-prod, productions, right? Because it's just image you running and getting a machine ready, right? So that's easy. Now, virtualization use cases, and there's a practical use case, by the way. Server consolidation. So running multiple workload on single physical layer to optimize the resource page. Suppose you have a bare metal, right? There you can actually run multiple virtual machines because it's have no OS, no overhead, right? But for a hosted OS, where you have a hosted hypervisor type 2, there if you go and try to run another virtual machine, you will see start panicking. Kernel will start panicking. Okay. Then you have disaster recovery. So disaster recovery is what? So you somehow got hacked, your data somehow got deleted. This kind of things are very common not so common, by the way. Common in the sense that can happen. It's common, not such common that it's happening every single day. Otherwise, every engineer, they will kick off. So disaster recovery. So creating a virtual replicas of critical system for fast recovery in that state of failure. So what happens, we create backup machine images. So if it's a very critical system and it's a stable mode, so of the stable version, we tend to create stable images, somehow something goes wrong, our stable image got distracted, got bad. We can quickly, shut down the existing that's gone bad, and we can revive the backup, which already have a stable state machine or stable state virtual image, which you can run. Okay, that's one of the very important feature. Okay. I think then is the application isolation. So separate application that are required separate. So that's just as a concept I was telling. If you have your own like one application running on say on a virtual machine, someone got hacked, someone got problem, your other application will not get affected. So that's kind of application isolation. Then development and testing. By now you know that you can create several environments for staging, production, pre-prod, and all that. So that's help you to make the development faster. Okay. Now, similar kind of benefit for the container we'll go through, and of course the use cases. So, containerization benefit, of course, lightweight and very fast. Containers very small images, small packages. Okay, so containers share the host operating system kernel, making them more lightweight and faster to start and compared to the virtual machines. So virtual machines, big OS, all the dependencies. Containers, small OS, a part of OS, and just whatever you already need. Maybe you need only the Python. You only have OS, necessary basic simple OS. Then you have the basic necessary Python application, so Python binary, and your code. That's it. Nothing else. So it's of course very small scale, right? Then the next point, portability and consistency. So containers, your packaging in such a way that it will run exact same way in any other virtual machine if you have this container software installed, right? So container package application and their dependencies together ensure consistent behavior across different environment, a different machine, different host. Okay. Then scalability. Containers can quickly and easily scale up and down to meet the changing demands, making them an ideal choice for the microservice architecture. So what happens, for example, Kubernetes, you are running one application. Suddenly there is a huge workload for the application. You can quickly spin up other, say, a copy of this particular one container so that you can, based on the workload, you can scale your application. So you're creating multiple copies which will serve the application need, right? That you can achieve through this Microsoft, this combination. And main benefit, I mean, last time, I mean, this previous slide, when we were talking about startup time is so small, right? And it's kind of near to none. Okay. So that way, if the startup time is kind of zero or very fraction of few seconds, is very beneficial to use for our scaling purposes, right? Then efficient resource usage. So using containerization allow us to better resource utilization, reduced overhead compared to traditional virtualization, of course, because with normal virtualization, you have a big OS, virtual OS, you have all software, but container is just running on a suppose on single core. I mean, so you have 8 cores, you can run on 8 cores as an individual containers. Okay. Then simplified application deployment. So containers enable streamlined deployment and updates of application, making DevOps practices much more efficient. So, what happens, there are many softwares, many services, ECS, EKS, which is ultimately Kubernetes, Measure, and a lot of other application container orchestration platform available, where it's very easy to deploy. Just mention, suppose you have a new image, just change the new image name. That's it. You will automatically detect the change, or you may trigger the change, it will replace the containers automatically. Right. Then you have the use cases. So first, I think most of the important use case is this microservices. So what is a microservice? We'll come to maybe later sessions. We're going to cover anyway. So microservice building and deploying application as a collection of small independent services that can be developed, tested, and scaled independently. That we call microservice. So, and why Docker coming at this in this particular phase? So just like I told you, in a single virtual machine, you can create multiple copies, right? And you can, of course, have multiple variety of copies. So one core, suppose is a 4-core machine. So one code you can run Python, another code you can run Java, another code you can run, say, something else application. So you can have this luxury of flexibility, right? And in microservices approach, kind of similar kind of idea, where you are developing application individually, isolatedly, and you are going to deploy and run this application individually or kind of isolation space, isolated space. Maybe there is an interconnection, but that you can achieve with containerization also, right? So microservices architecture is actually made more easy with the help of this containerization. Then you have continuous integration and continuous deployment, CI/CD. Now, streamlining the process of building, testing, and deploying. It's like using Docker, you can streamline process of building, testing, and deploy application. I think one of the very good example is the AWS code deploy, which is kind of running. It's you mention what exactly is the image where you want to you want to build your own software. For example, to run a Python application, you need to first get the source code from some GitHub repo. Then you create that particular application virtual environment. It's a VNV, virtual environment. Then you have the requirement.txt, right? For Python, you just have all these packages mentioned there. So it will go and simply install the packages inside the Docker. Okay, you're using a Docker to make the build. So inside the Docker file system, you already have the source code. You already have the say all the dependencies, and then you can, out of that particular content, you can run on any Docker if you want. And also you can create another Docker image from the particular build system, right? So you already have everything, simply create another Docker image. So you can achieve all this, like all this CI/CD continuous integration and deployment with the help from this containerization concepts. Okay, and not just not talking about the code build. Particularly, there are many softwares, okay, which help you to achieve this kind of stuff. Then application isolation. So running multiple instances of an application in an isolation to avoid conflicts and improve security. I think last I was talked about, right? In a single machine, if you have 4 core and running on each core separate machine, that kind of concept here. Okay. Then you have multi-cloud and hybrid cloud deployments. So deploying application across multiple cloud providers, combining on premises and cloud. Suppose you're running your application in container, and containers characteristics is that it will run exact same way how you package the application, be it on premise, be it cloud, be it anywhere else. Okay, that way you can of course achieve this multi-cloud and hybrid cloud use cases. So this is the benefit of this convention and its use cases. Okay. Okay. So now this is the, like, we understand the, like, what are the common stuff. Now think about what are the different stuff. Like what is the difference between the virtualization and containerization. Okay. So let's go with that one. Okay. So first is the resource utilization part. So virtualization requires separate operating system for each virtual machine, which can consume more resource. Like I was telling, like, why is so costly to use virtual, like in a single virtual machine, if you install another virtual machine, it's costly. This is the reason, because separate virtual machine require like separate consume more CPUs, more memory, more storage. But containers is very lightweight. Okay, and they can share resources of an existing host operating system. Okay, that's why it's more lightweight. It can run multiple copies of container, cool, no problem, like that. Then you have startup time. I think I was telling, right? Your normal machine or virtual machine, a virtualized machine, startup time takes a time. Okay, but containers are very lightweight. Only OS your application, nothing complicated. Of course, it'll boot faster, right? Now, management, virtual machines are managed by the hypervisor. By now, you already know that, which we don't do, by the way. It's the raw responsibility of the cloud to manage the hypervisor and manage the virtual machine. We manage after the virtual machines hand over to us. We update the patches, install software. That's our responsibility. Then if we run the containers, running container in Kubernetes or Virtualization, that is our responsibility. Okay. Then you have isolation level. Virtual machine provide stronger isolation between the instances. So what happens? You have EC2, one EC2 with you. Maybe your friend have another EC2. You cannot access your friend EC2, right? That kind of isolation is there. But containers share the same OS kernel. So kind of less restrictive, because see, virtual container, you have, suppose in a host network you're running your container. Since it's running on the host container, it and other, suppose container running on the machine, like where you install Docker and you're using the host or machines network, they can communicate with each other if you want to. So isolation is not like a foolproof isolation in this container case, but in virtual machines in general, It's a complete isolation you can achieve. Then the architecture part. So virtualization relies on the hypervisor to create virtual machines that mimic a physical server with its own operating system and application and resources. While as containerization utilizes a container runtime and to create containers and share the host OS kernel, but have an isolated user space of running the application device. So smaller scale, running on the only single host where you can have multiple containers, right? So architecture wise is also different. And of course, the main difference is that virtualized OS, virtual OS, virtual system managed by the hypervisor, containers managed by the containerization platform, Docker, Kubernetes, all the stuff. Okay. Use cases. Virtualization is ideal for running multiple diverse applications in a single physical server or consolidating a legacy application. So if you have a legacy application you want to run on, like say you're running your own machine, some application that you want to move to cloud or run on instance, then you create a virtual machine, you run your application, right? That's the thing. Now, for containerization, which is the more modern approach or modern application development practice, such as microservices and DevOps, where application are developed, built, tested. So for modern use cases, we have containers. For like very old legacy systems, or maybe running your containers, you need to run on a host or virtual host, right? There you need virtualization, virtual host. Okay, so these are the key differences. If in interview they ask you like what is the difference between virtual machine and container, you should say a single point that is like can help you to pass the interview. Virtualization, like virtual machines, use managed by the hypervisor, and container managed by the or convention managed by the container runtime. It's kind of Docker, CRI-O, misses all this. Okay, that's the key difference part. Okay, so I mean, I will not go to very depth. I will just go a scratch of this platform. I mean, scratch of this particular point that like what is the type of virtualization, because it will be too much if you go to every single point. But just understand, you already understand like what is virtualization. But in virtualization, you have hardware virtualization, you have operating system virtualization or containerization, and you have application virtualization. Like there is Microsoft App B, Critics App, or for example, you have this Oracle, some software is there, all that, right? We'll go to a very small deep dive here. So hardware level virtualization, or called platform or server virtualization. We call it by multiple names. Okay. Yeah. So let's go with the flow. So by now you understand there is virtualization. There is two type of virtualization, right? But sorry, there is two type of hardware virtualization we covered, but we didn't know exactly how many types of virtualization there. We're talking about, okay, virtualization, then only type 1, type 2. But that type 1, type 2 actually based on the is it hardware, is it operating system, is it application, based on that. So that's why I made a separate slide just to explain that there is three kind of virtualization. First one is the hardware level, second is the application layer, or sorry, operating system layer, and third one is the application level. Now let's understand this very carefully. First one is the hardware level. So in hardware virtualization, when you have a physical hardware and you are creating on top of physical hardware, you're creating virtual machines to allocate the resources. Like you have 4 CPUs, you have 8 GB RAM. We can divide it into 2 virtual machine having 2 CPU and 2 GB RAM, and another virtual machine, 2 CPU, 2 GB RAM. Or we can get 4 machines, 1 CPU, 1 GB RAM, like 4 virtual machines, each virtual machine having 1 CPU and 1 GB RAM. So we can divide all this and we can calculate on this in our brain or using any tools also, right? So that's the hardware virtualization, using whatever the hardware we have. What are the RAM? I don't have this one. My previous workflows had this. We have this physical RAM with this physical CPU. But you guys already know all that. Might have, in past you have configured your machines, right? So those you can isolate and create virtualization environment, right? And then it's coming, okay, there's like, what are the ways you can do virtual hardware virtualization? You already know type 1 is bare metal, where you have you brought a machine from the particular market and you have nothing installed, bare metal, and maybe it had there is one such software available which you can install and like nothingness or bare metal or like normal machine, like you install operating system, right? operating system used bare metal only, isn't it? So of course there will be other software which can be installed in bare metal machine, isn't it? That is a bare metal hypervisor, which getting installed in the fresh machine you bought from the market. Okay, nothing in it, right? Then hosted, which already have some platform, like say you bought a machine from market and you didn't install any hypervisor. First, you install maybe Windows or Ubuntu or Linux, right? Then you have your additional hypervisor software you install on top of the machine and to achieve the virtualization. Okay, that is a hardware level virtualization. Now what? Operating system level virtualization, or called containerization. So operating system virtualization involve creating isolated environment called containers, which share the same operating system kernel with other containers in the same host. Now, containers are more lightweight, as I was saying from the last few minutes, resource efficient to the VMs, because VMs heavy, too much stuff. Smaller VM, small resources, not so heavy. We can compare this container as a small VM, okay, which doesn't have this complicated things running. As do not require a separate OS or each instance, okay, for each instance. Now, container package application and their dependencies together, ensuring consistent behavior across the different environment. And popular container technologies include, I mean, we are talking about like what are the container software you have, what container runtime you have. You have Docker, you have Container D, you have CRI-O, and you can use this containerization runtimes with Kubernetes, with Docker Swarm, with Amazon ECS, right? So we have these things. Now, what is like application virtualization? So application virtualization abstract the application layer from underlying operating system. So what happened? You have your normal hardware machine. On top of that, you have your operating system. On top of that, you have another application layer. Okay. Then on that application layer, you are somehow trying to achieve the virtualization. Okay. That is this application level virtualization. So using application, you're achieving this. So in this type of virtualization, application are encapsulated and run within a virtual environment, which intercepts and redirect application request to the host OS. Now, this allow application to run on in different operating system hardware configuration without any modification and improvement, portability, or any compatibility. So just have this application, it will take care of everything. Okay. And this allow application to, I think, run this. Example of this application level virtualization is that AppV, Citrix, XenApp, VMware. So ultimately, what happens if you have a VMware app installed? So it will automatically isolate the resources, create everything for you, and from the application from this, suppose VMware, uh, you can simply go to connect with each virtual machine directly. You cannot directly interact with the operating system or command line. You have to particularly use application to interact with all this. That is the main difference between these two. Hardware, you can of course have bare metal, like say type 1 bare metal, type 2 hosted. For operating system, you have containers. For application virtualization, you have application which handles virtualization work for you. So this is the main types of virtualization. Virtual technologies and tools. I will not bore you guys. Again, it's not for all. You already know what is the bare metal mean. You already know the hosted mean. It's just a software, okay? Like say for type 1, you have VMware XACI or ES11, then Microsoft Hyper-V, then KVM or kernel virtualization. It's open source actually, by the way, that we are available for any Ubuntu machine. Then Citrix, formerly known as Zen Server, a hypervisor for the Zen project. So these are things that are available, mostly getting utilized for the cloud, cloud data centers and all that. Okay. For type 2 also, the VMware Workstation, Oracle, type 2 actually the one that we are using as a hosted OS. Also, you can use, we can set up a VMware Workstation for maybe a client, maybe Oracle VirtualBox for our use cases, or parallel desktop for our use cases, say solution for Mac, enabling users to run Windows and Linux, VM on Mac system. So that is kind of for us. But type 1 specifically for bare metal, even though we are getting bare metal solutions, we don't usually handle all this stuff. Okay, until unless you are actually expert on this, setting up this, so VM software, or say Microsoft have a KVM, again, it's come with the Linux package these days. Citrix, for example, now there are a few positions open as Citrix engineer. So then you have this requirement. Otherwise, you don't. Okay. Usually we deal with the type 2. Okay. Bare metal also, if you actually have the requirement. That's why I'm saying bare metal is a use case when you're expert, you know what you're doing, you have a very greater depth of knowledge, you are going to set up by yourself, then bare metal. Type 2, already most of the stuff is set up. It's more cases you are just enhancing the features, or you're running some stuff. Then you have this type 2. Okay, I will not go to depth because this is very opinionated things that you want to cover. Just know these are the software available. If you're going to join any particular cloud company, AWS and Azure, GCP, then you might this level of knowledge. Okay. Okay. Again, the similar stuff that for what are the popular virtualization platforms? Like you guys already know about VMware. So VMware, the software, VMware ESXi, type 1 bare metal hypervisor, VMware vSphere. It's a suite of virtualization product that includes the ESXi. Then VMware Workstation, a type 2 that is hosted hypervisor that run on Windows and Linux system, allow users to create and manage virtual machines. Then Microsoft VR, it's a Hyper-V virtualization platform developed and managed by Microsoft, integrated into Windows operating system. Okay. So and the key Hyper-V product, like Hyper-V for Windows Server and Hyper-V, like out of this Microsoft Hyper-V, you have two subdivisions: Hyper-V for Windows Server and Hyper-V Server, which is the standalone version. Okay. Then you have Oracle VirtualBox. So I think Oracle VirtualBox is actually the one I was using when I was learning few years back, on this virtual machines, how you can, in MacBook, you can have Windows or Linux. Those days, actually, I was using Oracle VirtualBox a lot. So where I just install this open source application, then I get somehow some images, and then simply run it, do some kind of cool stuff, and then shut it down because my machine got going to overheat. So much thing to running, right? So Oracle Virtual was good thing to learn. Then you have KVM, or kernel based virtual machine. Now this KVM actually I didn't cover in my last slide because I'm going to cover here in very detail. That's the reason. So yeah, KVM is a open source virtualization platform that is integrated into Linux kernel. So if you have a Ubuntu desktop OS or Ubuntu server, most probably you already have this KVM pre-installed, okay, or this platform pre-installed. Now, turning Linux, it will help you turning your Linux into type 1 bare metal hypervisor, okay. Then KVM support a wide variety of guest operating system and offer features like live migration, virtual networking, storage management, and KVM commonly used in cloud computing environment and in the foundation of several commercial virtualization products. Now, this KVM looks smaller the way I'm defining, but it's actually a very big stuff in Linux. Many cases, if you want to achieve virtualization, you may be already using this LVM behind the scene. Okay. Now, this thing you don't have to remember, just maybe the KVM part you should try to remember. But other two stuff is okay. VirtualBox you can install and experiment with it. It will be helpful for your own learning of this virtual machines part. Okay. Any question on this type of popular virtualization platforms? I think like an interviewer might ask you. In that perspective, you have to tell the name of this, VMware, Oracle VirtualBox, KVM, these things. Okay. Otherwise, they will not say. Like Microsoft VM, they will just say give some example names. That's why. Then only you have to say. But this KVM, if you're focusing on, say, cloud architect kind of positions, maybe or DevOps architect position, there this KVM might come. Again, very rare cases. It will not like come everything. Okay. Now, what are the virtual machine management? Now there is vSphere, there is Promox virtual machine or Promox V, there is Overt. These are the virtualization management platform which you can use to manage your virtual machine. Now, this VMware actually enterprise grade virtualization platform developed by VMware. This Proxmox. I'm very bad at present pronunciation. Now, Proxmox V is an open source virtualization platform, combines both KVM and container-based virtualization, or is LXC, and under a single web interface. Then there is Overt, okay, or whatever it is, Overt. Now, Overt is an open source virtualization management platform built on KVM. I was saying KVM is a big deal. Using KVM, a lot of other software, a lot of other platform develop. So this and it's a design for large scale enterprise environments. Overt provides a comprehensive set of features that manages VM, including live migration, high availability, storage management. So all these things you can achieve with this virtual management software. Okay, I'm not going too deep because hardly you're going to use any of this. Yes, containerization technologies and tools. So I think we are slowly going deep into this containerization thing, because that is the goal, right? Learning containerization in a way that you never forget, or you can pass any interviews if it's any question related to containerization. Now, what are the containers again? Containers are a lightweight, portable units used to package application and their dependencies, allowing them to run consistently across different environment. So what happening in a container? You already have a OS, so Ubuntu or whatever it is. You already have the code. You already have the binaries to run the code and everything. And ultimately, you are giving instructions to the image, then how that image going to, how that container going to function. So you're giving everything, whatever required to run the container, you're putting inside the container image, right? And this container platform is running it, or container runtimers are running. We'll come to what is container runtime in this slide only. Okay. Now, this container, you learn, okay, containers, lightweight, portable units, a portable image that used to package application and their dependencies, allowing them to run consistently across different platforms. They share the host host operating system kernel, but have isolated user space for running application. Containers runtime are responsible for managing. Now, what is the container runtime? So this container runtime are responsible for managing the lifecycle of a containers, including the creation, execution, and deletion. So there are softwares, say Docker, Containerizaton, CRI-O. Of course, these are the runtimes. So the software we are calling the runtime as well. So suppose this Docker, which is a very vast software, which have the capability, of course, to create the image and run that container image as a container. So this container platform, the container runtimes allow you to create the container, to manage the container and execute anything that you like, and delete the container. That is the main functionality of any container platform or container runtimes. Okay. Now, let's go with the bit introductions. What is a Docker? So Docker is most widely used container runtime that has a synonymous with container. So previously, suppose saying container, oh, are you talking about Docker? Or suppose saying Docker, they're talking about, okay, I created a Docker image. We usually thought, okay, this guy created a container image.
Same my question, which I asked. Yeah.
Yeah, that was the days before this container D and CRI-O. I think lately you might have heard a news which created a havoc in the container community, where Kubernetes dropped support for Docker. I think some of you might have heard.
Yes. Yes.
What is all the like? See, they're not actually remove the support. They have the support for container runtime. So it's a common platform they created. Like you have a container image that follow a specific guidelines, we will support that. Develop in Docker, develop in Containerd, develop in CRI-O. We don't care. Just give us a container image that is properly followed a guideline. Okay. What is the guideline? How implemented? You have to wait till next week, because I don't want to overcomplicate you guys. Just think that Docker previously was a synonymous with container, but now we means Docker. Docker is just like any other platform to create a container image and run the containers. That you should imprint in your mind. Okay. Now, it provides a simple command line interface and a rich ecosystem of tools for building, packaging, and distributing container images. Now, Docker simplifies the process of creating and managing containers, making it easy for developers and system administrators to adapt to this configuration. So before Docker, it was kind of a bit complicated. I mean, I actually tried even before Docker. I was one of the guys who use containerization before even Docker. And to be used, I use LXC, which is super complicated, to be honest. At that time of like, I'm not a pro, I'm not a, it's a simple learner. I was hearing about a cool technology where giving Docker containerization. Now, why? What the hell is containerization? It's a lot of question of mine. So I go and try it. Ultimately, I give up. See, it's beyond my capability. I put my hands up. Then there is Docker came, which make me fall in love with this containerization. So using Docker, I think it's very easy to create container images. It's very easy to run on different Docker, different application, and running on different platforms. So easy. That's how Docker actually become a de facto leader in containerization. Now, like everything started with open source, and then they start charging money. Like everywhere the same stuff, just like say OpenAI, for example. They start as a free, then they become a paid guys, right? So Docker also started kind of similar way, in a way of making it free, making it open to everyone. But somehow down the line they change their course of path. They become some kind of profitable business. Of course doing great work anyway. So then there is requirement came, okay, these guys becoming profit oriented. Let's have the competition ready. Then we have this container D. Okay. What is container D? Container D is the high performance, lightweight container runtime that is designed to be embedded in larger systems. Originally part of the Docker project. Yeah. Now we're coming to it, right? So originally part of the Docker project, Container D has become standalone project under the Cloud Native Computing Foundation. See, the moment some guys notice, hey, Docker becoming profit-oriented business, we cannot be with them if you want to become an open source guy. But any project needs funding. Okay, like this entire setup need money, right? Like I need to pay electricity bill. So those guys are working on this projects also need money. So and they were heavily dependent on this Docker project. But concerning that Docker might become like already becoming privatized, um, it is not good to continue container project as part of the Docker, but need funding, right? Then there is Cloud Native Computing Foundation, which give very good amount of funding to the open source projects. Now, Containerd become such a great open source project, just kind of a rival to Docker, even though it was a part of Docker project, but it become rival to Docker. And now these days, if you go to run any application image in Kubernetes, they prefer actually you have a Containerd or CRI-O image other than Docker. Okay. Of course, there are a lot of very good events. So it's open source. That's a good part, I will say. Now, it provides core container lifecycle management features such as image transfer, container execution, then storage management, and Containerd is used by Docker and Kubernetes as the default container runtime. See, Docker guys also started using Containerd, but now I think last time I heard from these Docker captains, Docker is having its own system for optimized stuff, but it will support this open image kind of guidelines. Okay, now let's come to CRI-O. Now CRI-O is is an implementation of Kubernetes container runtime interface that optimized for running container in Kubernetes environment. Okay, and it's a lightweight alternative to Docker and Containerd, specifically designed for Kubernetes cluster. Now, CRI-O supports same container image format, runtime features such as Docker, making it compatible with existing container workflows. Because you cannot suddenly come and develop an image which can only run in like Kubernetes. You have to develop in such a way it can run on any container platform. Like Suppose I am running currently on this Kubernetes platform, but maybe in the future, maybe I want to run in ECS, maybe other, maybe some proprietary other software you want to run container where you can run on Kubernetes. Then we need an image that support that. That's why any image that you talk about, any image developed by Docker or container or say any container image we get as an output from any platform, it follow the open image guidelines. Okay. Again, we'll come to that in the next session because I don't want to confuse you guys more. But think that these are the very famous container runtime that actually getting used in the real world. Okay. Okay. So now, like, what are the popular container orchestration? Now, orchestration, it's simple, very basic sense means managing stuff. Okay. And when you're saying container orchestration means some software managing containers. Okay. So, and what is the container orchestration is implying to? So container orchestration implying so that involving managing and deploying, scaling, operation of containerized application across multiple hosts. Orchestration ensures that containers are running as expected, handle failures, and manages the resource allocation. Now, some popular container platforms, like orchestration platform, are Kubernetes, Dockerfile, and Amazon ECS. It's simply a software managing container, nothing more complicated on that. Okay. Now there are many software like Kubernetes, then there is Docker Swarm, Amazon ECS, maybe AKS, Azure AKS, and a lot of other software, right? Now, we will not go through every single tool. We just go to the most famous one. That's I think it's most famous. It's biased to be honest. So first one is the Kubernetes. It's open source project by Google. Is most widely used container orchestration platform. It offers advanced features in for managing container deployments, such as auto scaling, rolling updates, self healing. Kubernetes can run, run on premises, on cloud, on hybrid environment. Has a rich ecosystem of tools and integrations. It's open source, right? So many. It's a huge ecosystem with huge number of plugins, functionality extensions which you can extend. Key features: declarative configuration. You have a YML file or even a JSON file where you can use to create containers, run containers, manage containers, configure networking, and do other complicated stuff. Then horizontal scaling. It supports the horizontal scaling where you can suppose based on say you for some morning no demand, you're running one application copy. In afternoon, many people came, say the student, for example, many people are giving order. Then it created a multiple copy of the same application. So multiple pods. We'll come to the pods and everything. Later session when we cover the Kubernetes anyway. But it's a scale horizon. You can create a copy of single application, like multiple copies, and distribute the load between multiple copies so that platform is the application will be stable and can serve more users properly. Okay. It support the load balancing. I already told that. So it's clearly support load balancing and service discovery. What is load balancing? What is service discovery? We'll learn about that very, very advanced way in the cloud session, which is, I think, after 1 week is starting. So yeah. Then you have rolling updates and rollbacks. So rolling updates means suppose you have 10 copy running. Okay. And you have made some modification in code, maybe improve some code. Now that code change actually have to deploy in 10 particular copies of your instance or 10 copy of any application, right? 10 copies need to be updated. You can suddenly shut down all these 10 application, let's say containers, and just back up them again, but it will result a downtime. And customers hate downtime. Engineers hate downtime. Clients hate, everyone hate downtime. That's why you have this rolling updates. So rolling updates, what will do? Maybe one container at a time, or maybe 2 container at a time, maybe 3 container at a time. So you are 1 by 1, or maybe 3 by 3. You are rolling the deployments, taking it down, update, again, pull it back, right? That way. Now, what is the rollback then? Suppose while deploying the changes to this one particular container, you found out, okay, something gone wrong. Maybe the container not starting up, some problem and all this problem, right? Then there has to be a rollback mechanism, right? which will roll it back to the last stable build, right? So Kubernetes have this kind of feature. If something not working, then if you configure properly, it will roll back to the previous stable build. Or any build that you think is stable. Okay. Then you have this sorry, I mean completed the other things. Persistence, storage, and management. So what happens, in containers, you create a container, you run a container, and you make some changes in the container. If you shut down the container, anything that you work inside the container file system will get lost because it's ephemeral. It will forget, it will not remember. Now, to make sure that you are working, say, log file, maybe another very important database things, you want to store data permanently, okay? Or you want to persist the data till the time you don't want it anymore, okay? So it's your wish that up to that time. Then you need persistent storage. And Kubernetes support this persistent storage mechanism through different provider of plugins. Again, don't complicate. We'll come to that. For example, Elastic block storage, maybe Google storage, maybe anything ELB and all the stuff. We'll come to that one later on. Okay. So these are the features we have. Then we have Docker Swarm. So Docker Swarm is a Docker native containerization solution tightly integrated with the Docker ecosystem. It's easier to set up and manage than Kubernetes. Of course, it's not that complicated, making it suitable for smaller scale deployments and users already familiar with Docker. Now, Docker Swarm focuses on simplicity, ease of use while providing the essential orchestration features. Like whatever you need, basically, small only scale system, you should never use, to be honest, Docker Swarm. But if your team doesn't have the willingness to learn Kubernetes, or they think it's too complicated, those kind of scenarios, is like they want to manage by themselves this orchestration, but don't want to go to Kubernetes, then only Docker Swarm makes sense. And of course, they have some Docker knowledge. Now, key features: easy to set up and management, of course. Then service discovery and load balancing is supported, rolling updates, scaling and replication, and then you have integration with Docker CLI. So it's kind of very tightly integrated with Docker CLI and Docker Compose. Okay. Then you have 3, that is Amazon Elastic Container Service, or Amazon ECS. Now, Amazon ECS is a fully managed container orchestration platform or service that is given by AWS. It supports both Docker and AWS Fargate, which is a serverless container engine for deploying, managing of containers. And ECS simplify container management of AWS infrastructure and integrates with Amazon services like Elastic Load Balancing, RDS, and all this out of the box. They already do all the stuff. Okay. Now, key features of this Amazon ECS is fully managed service. You don't worry about maintaining a software service. You go supply the image, create a definition, run the application, and that's it. Okay. Then integrating with AWS services is very tightly. It's an AWS service, right? So by that nature, of course, it will be very easy to integrate with other AWS services. Okay. Support Docker and Fargate. So it's maybe a Docker part. If you have a Docker image, it will support it. Or any open image kind, any popular platforms image, if you have, it will support it. Then you have a task definition and service configuration. So you can define the task configuration, what is supposed to do, that one. And service configuration, suppose it's a multiple application service, or it's a service. Service is what? Service should not go down or should be auto recoverable. Not a task you are running, you're going down. Service will stay up until you want it. Okay. Then scaling and load balancing. It's very tightly integrated AWS load balancer. So it's very easy to set up and all that. Okay. So that is the popular orchestration platforms. Okay. So we learn about the basic container orchestration. Now let's jump to the container registries. And how many slides are remaining? Oh my God, too many slides. We'll go a bit faster now. Okay. So yeah, container registries, we have Docker Hub, Google Container Registry, and ECR and QA.io. I don't use this, but it's a good platform. Many use it. That's why I included. It's by Red Hat, by the way. So Docker Hub is by Docker. It's the biggest image repository or container images repository. Okay. Then you have Google Container Repository. It's a private and managed, private managed. So if you want to host private container images, then you should go for this Google Container Registry. Then you have the Amazon Elastic Container Registry, ECR. It's fully managed by Amazon. If you want private, you can go for this ECR. Also, now they are supporting public ECR images, which is kind of, they want to be alternative to Docker Hub, guys. Okay, so now you have the private and public, both available in Amazon ECR. Then you have the CRI-O. So CRI-O is the container registry service by Red Hat, offer private container image storage and advanced feature like automate bail security scanning. Like everybody, they say advanced feature, but every single registry or container registry provider giving you automatic scanning, building all these features. Okay. Yeah, just if you have doubt, I'll just go to the definition a bit first. Container registries are services that store and distribute the container images. Suppose you have develop a container image, right? You have to distribute that image with your team. You have to distribute such a way, to share such a way that it can run on, see, you're developing image locally. That image you're supposed to run in remote servers or AWS Kubernetes EKS, or maybe normal instance, or maybe ECS. So you need to store somewhere remotely, so that remote instances can pull the image whenever required. That is what we call image repository. Now, this go to the definition a bit, I will understand anyway. So they enable users to share and deploy containerized application easily and consistently over many environment. Registries can be public, private, or a combination of both. For example, ECR, depending on the requirements. And of course, Docker have also give the private and public both. So yes, same are. Some popular container registries, as this Docker Hub, Google Container Registry, Amazon ECR, and CRI-O. Okay. So anyone have any doubt for this container registry? I don't think we'll have any. It's just straightforward.
What kind of container registries will be for container D or Docker? So the other
Doesn't
one.
matter. Container image, as I say, everyone supports similar. Make the image that is final image. Can be done anywhere. So any Docker registry, I'm sorry, any container registry can store any image.
Okay. And can I use like, let's say if I'm using ECS, for example, then am I supposed to use only ECR as my Docker container registry, or I can pick from Docker Hub or
any is fine.
Okay. Okay. Cool.
Okay. Any is fine here. No worries. I think that's there. So you can run any, you can store any container image in any container registry. No problem. If it's a public, you can store publicly. If it's private, you have to pay for this. That's the only difference. Okay. Now, managing and monitoring the containers. There are many tools and softwares, for example, Prometheus, Grafana, ELK stack, that will help you to monitor and manage this. I will say the monitoring part. It's mainly to monitor the container platform. Managing, you usually use the orchestration software to manage that. I say managing, but somewhat to manage also you need to understand what is the data, understand the data, understand the stats, then you manage, right? That is you do by this Prometheus, which is open source monitoring and alerting toolkit. Then you have Grafana, it's more of a visualization tool. Then you have ELK stack, it's to both store logs, both visualize the logs, and alerting also altogether. Okay, I will not go to very deep because I'll go to advanced session. We'll go to very deep on this.
Sandip, do you have these sessions means for the individual topics at later point of time? This
not individual, because too many things, right? If you go very individually, it'll be a problem. But yeah, videos available. My videos available on Prometheus, Grafana, ELK coming. Videos will be available. Okay, as a everyone thing. Okay, best practices. I will go very quickly. Okay, because at the beginning, you guys are Ghanta, we will check for best practices. You guys will just want to learn the basic stuff. So these things I'm sharing, like what should be the virtual machine sizing and the best practices for virtualization. Like you should understand the application requirement. Based on the application requirement, you should allocate CPU, memory, storage, network, designing and all. Then balance resources on the host. You should keep monitoring the stuff. Then do all the stuff. Again, if I even explain to you, that doesn't make sense, because you have not become that practical yet. The moment you start thinking more practically as we move forward to the course, then this will start making sense. But good to know. Just know that you don't have to remember it. Just know it. Okay. Same goes for the storage of management also. Like you should be planning the storage, how you have to store, where you want to store, then tiering, because every storage has this SSD, HDD based on the cost, performance. You should choose where you want to store it. Provisioning, like do you want one on demand storage, or you want to provision the storage, all the stuff. Then compressing, like if you want to compress any particular data on storage, then snapshot backup management. So every cloud platform now give you ways to snapshot it and backup it that you also want. Then storage monitoring analytics. So for example, CloudWatch in AWS give you this kind of storage monitoring. Other tools are there, but you have to choose from them. Then you have storage maintenance and updates. If it's a kind of managed storage service, it's of course managed by cloud service provider, but you are managing, then you have software and you should be managing that. Then data archiving and lifecycle management. So you're keeping your backup data, right? And then you're archiving and storing somewhere. If you don't need it, or maybe you want to move it to more less costly backup system, you should have this kind of auto life cycling there. Okay. This is what you're trying to make point here. Then you have networking and security. So of course, virtual machines kind of running behind the networks, right? So you are behind the network connecting. So have this network segmentation and subnets, right? Use the virtual LAN or VLAN. Then use the network security firewall to only allow your IP, maybe not other people IPs. Then you have intrusion detection. Suppose some hacker doing very mischievous stuff, you should have some kind of intrusion detection, like IPS system, IDS system. Then encryption is very good practice to encrypt your data, encrypt your network security and all that, like using strong encryption keys. Okay. Then you have this secure remote access or SSH. So suppose use certification based certificate key based authentication. It will be better instead of username password for the remote connection and all. Then you have vulnerability scanning and pen testing. So you should have some kind of, say, CRI-OS, or a lot of tools are available. You can try to try to take the vulnerability scan from vulnerability and try to penetrate your own system. Okay, good practice. Then you have security policies and best practice. Of course, every single service that you want to use, it has own best practices. You should want to check it with the documentation and follow it. Okay. I know I'm very quick because this you guys never going to remember anyway, until unless you're going for interview. Okay. Then you have the backup and disaster recovery strategies, like identify critical system on the data that you want to backup. Then use backup regularly, at least store the backup for 14-15 days. Then offsite and inner storage, like where to keep the copies, how to keep the copies. Then recovery point objective. Yeah, no, this is very important. I think I described this one in some past session. So recovery point objective and recovery time objective. So define your RPO and RTO goals based on your maximum organization tolerance of the data and loss. So what is RPO? That is recovery point objective is a maximum acceptable amount of data loss. Like how much can you lose, right? So and measures in time, and RTO goals based on the recovery time objective is the goal based on organization's tolerance of data loss. Sorry, I think it is the maximum acceptable time to restore. Like your system going down, how much quickly can you restore your system? That is the RTO. How much data you lose is acceptable. That is RPO, recovery point objective. This is you're going to be asked in the interviews. So understand very. If you have any doubt, let me know. We'll talk on that. If you're very clear, it's fine. Now there is test and validate backup. Of course, when you're keeping the backups or doing the backup, have a checksum to make sure what you're backing up and what your final backup file is, the checksum matching or not. Okay. Then you have the disaster recovery and plan. If something happened, what are your disaster recovery plan? You should plan it beforehand. Okay. Then you have regular updates and documentation. So keep your backup ready, and whatever service you're using, maybe the documentation you are keeping for your guys should be a very updated one. Then training and awareness. Like security is not an individual job or not a single guy's job. The team has to be taught properly how to maintain the security of a system. That should be some training and activities, learning activities should be there. Okay. We covered up to the virtualization part. Now, what are the best practices for the containerization? So for container management, container optimization, you should use the base image properly, not the hacked one. Use the original official sources. That's what we're talking about. Employ multi-stage builds. So if you're going to make a container build for production system, use multi-stage builds. Then don't add too much commands. Okay, if you have too much commands, why not you use a shell script to make it compact in a single command execution? This is why you are reducing the number of layers in the Docker system, or not Docker system, container system. Then clean up after installation. So if you have anyway, if you use this multi-stage builds, you're not going to have issue with this this cleanup problems, because ultimate final production image in a that multi-level build, that multi-stage, that stage, production stage, you will have only final binaries, and all the dev stage, all this testing builds going to get discarded. Okay, so anyway, it's good to clean up temporary files, unnecessary packages after installing dependencies in a Dockerfile. Now, then you have versioning and logging. So use proper versioning and tagging scheme for your Docker images, or sorry, container images, not Docker images, to help maintain organization, traceability, and control over your image repository, and as well as simplifies the deployment process as well. So if you know what you're going to deploy, it's easy, right? So have proper naming and all that there. Then you have scan images for vulnerabilities. Now each container platform now supports or container history also now supports vulnerability scanning. So it's a feature, sometime by default enabled, sometime if they're not enabled by default, you can enable and you can check for that. Then if you see a problem in one container image, you rectify it, you fix it anyhow that's possible, right? Then monitor image usage and updates. Monitor the usage update of your container image to identify outdated or unused images. Unused image you want to delete it. For outdated, you want to update the images, right? Then regularly review and optimize Dockerfiles. Specifically, while I was working with a guy from Apple, he's a team leader of Apple, okay, and his particular job is to actually review the Docker files. Nothing else is there. Is the DevOps engineer subset guy, whose only job was just to review regularly any security vulnerability CVCs, compare CVCs and fix it, and optimize the Docker files. So those kind of stuff also you have to do as part of a regular job. Okay, then the next is the best practices for convention networking and security consideration. Now, networking, like while designing network, you should be isolating it, secure container communication. If it's a container to container communication, it should be secure using, say, MTLS, for example. Then implement container network, can implement network security policies. Then secure container images using, say, Clear, Twitchy, Adore, and other patches. If you want to include it, you can include it there. Then use API gateway, ingress control. You should not never actually allow direct access to Docker port and all. Instead, there should be an API gateway which will redirect traffic from the outer internet or ingress to the Docker. Then you have container runtime security, authentication and authorization. Implement robust authentication and authorization mechanism to accessing container services. Utilize standards such as OAuth2, OpenID Connect, role-based access system, all this to manage access container system. Then you have this container runtime security used to like App Armor, Secomp, Gvisor to select to secure your container runtime. Limit the action containers perform on the host to make sure your host is secure. Now then monitoring logging, implement monitoring and logging solution, just Prometheus, Grafana, ELS stack to track container performance and resource usage and security event. Then you have regular update and patching. You already know why it's important to make sure your image is not out of date. Make sure that your image work as expected. It have less vulnerabilities. You should be using that. Then you have monitoring and logging. I will not go to very much details. Anyway, you understand there is, application, the performance monitoring is there. Alerting should be there. Log should be getting collected for analyze and all. Monitoring should be there using Sega, Fana, Prometheus, all this stuff you have to do. Okay. I think this is the part you guys are waiting for last 2 hours. Docker. So now let's understand Docker. We'll go to a not too much deep dive, just a bit deep dive, because next week we're going to go to very Docker file system, networking, blah blah blah. So much things are there. Okay. So just for this introductory session, I want to cover Docker a bit so that we can complete by 1:30 at least. So Docker is an open source platform that simplifies the process of developing, shipping, and running application by using containerization technology, allows developer to package application with all dependencies and configure into single image or a self-contained unit, which can then run consistently across various platform, environments, host, machines, whatever. Docker has gained widespread popularity due to its use, portability, and flexibility. Now, Docker is just a open source platform. I think open source is not anymore. I'll remove this open source part anyway. But it simplifies the process of course, developing, shipping, and running application by using containerization technology. Help us make container images, which you can run as a container, by the way. Now, key concept architecture will come to the next week anyway, but just I want to cover the basic stuff here. What is the Docker engine? Now, Docker engine is a core component responsible building, running, and managing containers. It comprises of Docker daemon or Docker D, a REST API, and a command line interface. Again, don't go to very deep for today's session. Next week, we're going to go through the architecture of Docker, how each component are linked together and all that. Just understand these things are there. So it will be good for you to next session. Okay. Then you have a Docker file. Now, Docker file is actually a script containing instruction to build a Docker image. And it defines the base image, application code, dependencies, configuration, anything necessary to run the application or run the application in any environment. Okay. Then you have the Docker image. So Docker image is a lightweight, portable, self-sufficient snapshot of an application and its dependencies. Images are built from Dockerfile and can be stored in any container registry such as Docker Hub, such as private registry, such as anywhere you want to store it. Okay. Now Docker Hub you might already covered in the last few slides, slide back, where it's a cloud-based container registry where you store your Docker images. Then you have Docker Compose. So Docker Compose is actually a tool for defining and running multi-container Docker application using a YAML file. Suppose you want to run multiple Docker in your system or anywhere else, then you want to use Docker Compose. Okay. Then it simplifies the management of a complex application stack by allowing developers to define services, network, ports, and all that thing. Again, don't complicate yourself. Just a software provided by Docker to run multiple container at once. That's it. Now, benefits of using Docker. So Docker's using consistency and redundability, which is container package all the dependencies and configuration required to run the application, ensuring it run consistently across different environments, development, production, testing, for example. Then isolation and resource control. Containers provide isolation and resource control, which help prevent conflicting between applications. I think one question was there. Suppose you have, can we run Python, Node, or Go app all together? But it will start conflicting sooner or later. I mean, so a lot of problems. So using isolation, you can run multiple images, right? Using that kind of way you're isolating application, you are enabling for microservices approach. Then you have rapid deployment and testing. So containers are lightweight, start very quickly. Startup time is very low, and enable us for rapid deployment and scaling application. For scaling, we need something that is very quickly going up to use, right? Those cases. Then you have efficient resource utilization. So containers can share the host operating system kernel and resources, making them more efficient than traditional virtual machines in terms of resource consumption and performance. Okay. These are the basic Docker introduction. It's just a software we use to create container images that can run, of course, by Docker or any other container runtimes or container orchestration, like Kubernetes, ECAs or anywhere else. So
okay,
what happens? So in order to create a Docker image, you need what? A file called Dockerfile. Okay. And Dockerfile look like this. Okay. Which have like from a particular base image, you select the work directory where your application code will exist. You first copy the requirements or any packages like JSON or YAML, using which you first install the dependencies, then run pip, like Python, for example, installing the all the dependencies. You're copying all the codes, exposing port 5000. It can be any port that you want to expose, and then run the application, right? Like this, in plus cap. So what we are coming at, that this is the Docker file using which you can create Docker image, which you can run on any platform. Okay. So what this tool, let me just quickly.
Sorry, question, Sandeep. So when you say you're creating an image, that will be the combination of code plus the underneath server which needs to be running in as part, becoming a Docker image, or how?
So ultimately, see, Docker itself have everything. I mean, if your application need a server, then inside Docker image you should have the server.
Okay.
Okay. So for example, Python app, you're using Flask or any Python app, right? You're running the Python app. Python app itself is a server.
For Python, you may not need it. Maybe for Spring Boot. I mean, for
Spring Boot. For example, front-end application. So you are running a front-end application, right?
So I'm referring to this example. I'm referring with the front-end one. So they were having Tomcat image.
Yeah, maybe Nginx, Tomcat, whatever it is.
And I was confused because of that. That
okay,
if it is built,
then you see, the from image should be could be anything, by the way, but should be Nginx. Okay, so from Nginx something, then create say www something where, or say docs based on the what image you're using. Then you copy everything that you like, not everything. You should use a copy package JSON. Then install the using npm install or say whatever yum install, whatever it is. Then you copy entire code, then you expose the 3000 or 480, whatever it is, and then you run the application. Okay, that's a pretty basic way. Now, what this is and how we'll discuss that one. Okay. Just before that, I mean, yeah, that is the next step anyway. So yeah, now we're going to discuss this Docker file. Now, what is the Docker file? Let me quickly come. Oh, I have to run the Docker, by the way. So Docker. You guys can see the entire screen, right?
Yes.
Okay. It will be pretty quick, I know. He's already becoming more than 2 hours. So many things to learn, right? And we have limited 1 week. I mean, sorry, in a week I have 1 day. That is the reason I want to cover so many things in a single day. Okay, so I hope you guys have the Docker ready. You should be. So yeah, the Docker file is a script. Like, what is a Docker file? The Docker file is a script that contain instruction for building Docker image. Each instruction Docker file create a new layer. So always remember that file. Every command that you're running in a Docker file create a new layer, which I will suggest avoid or say do as few as possible. Don't add too much layer. It will make your layer more heavy or your container more heavy. Instead, you should use a shell script. If you want to run so many script, use a shell script. No, that's better. Shell script and do run there. That's much better concept. Okay. So a Docker file is a script that contains instructions for building Docker image. Each instruction in the Docker file get a new layer in the final image. The layer can catch it and reuse if possible or if needed, which makes building Docker image fast and efficient. So if you build one image now, if you try to build the same image or similar image again, it will be way faster because Docker catches each layer. So if it's find the common stuff, it will be faster to build. Now, each Docker file have this command list. Okay, this command list. Let's see. This from specifies the base image as a starting point of Docker image. For example, from Python 3.9 specifies the image should be based on this official Python 3.9 image with a slim version of the Debian operating system. Okay. Then we have this copy or add command, Now, what this copy or add command does, it copies the files from your host machine. So from your local machine, it copying your code or file to the Docker image. So Docker image is kind of a container, say in a folder, for example, that's easy to understand. Your code is in another folder, your Docker image is another folder. So what this copy command does behind the scene, it copy from your code where you have the files where you're running this this Docker file, and copy that to the Docker this container folders, whatever some consider you think there's a folder, it copies that this folder to that particular file or folder to another file or folder. Okay. So this copies a file from one host machine to the Docker image. For example, copy app.py, then app copies from this app.py from this host machine to this main machine, right? Okay. So that you now, that is the copy command now. Run command is running a command. Suppose you have the dependencies, right? And this dependencies needs to be installed inside this container image so that you don't have to run that particular, you don't have to reinstall every time. It's one time installed in this image, like in your machine, for example, in a normal machine, you install Python, you install all the dependencies, you don't repeat it or you don't do it every time that you want to run your application, right? So same way in the container, you only one time you run this particular, say, dependencies and everything as a shell script or whatever it is, to way to run it. And that's it. Next time when you start the container, it don't have to run and install every single stuff again. It will take a lot of time, right? But if you already have everything that your application need to run inside the container image, then it saves the time, isn't it? Then the run command used to run shell script or any command that you want to run. For example, run apt update and apt get installed. Then curl install the curl package, for example. Then work directory. Now, this sets the work directory for the commands to follow in the Dockerfile. For example, work directory, that's app set the working directory to be app. Now, what is this working directory? So if you're a Linux user, for example, you log in and you see, if you go to home directory, like this, for example, go to show the terminal. See, pwd, it's my home directory. See, user Sandip Das. So when application try to run, by default, when it's starting, by default, OS is starting, where it should look at first or go first. This is where you should go first, the working directory. So this working directory you can set. Usually you should set, like in the working directory itself, you will copy your application code there to run application, to do any kind of operation that you want. Okay. Then you have this CMD or entry point. Now, to start your application, there should be some command. Say Python space app.py or Python, then Flask app. Right? Or maybe just simply run the Flask app. Flask, then the Flask app. For example, this, right? Here you are simply running Flask command, right? Flask command, and then run, then the host where you want to run. Right. So this command need to be like, there has to be some starting script, right? So this CMD or entry point command specified the command to run when the Docker image is run as a container. So Docker image is the image, say kind of, it's a car. For example, Docker image is a car. The moment you go inside the car and you start it, it's turned into a moving car, right? So this container is a moving car. You have to still start, like start the engine and all that, right? So that engine starting part is this CMD or entry point, where the moment they understand, okay, this is the starting, this is a script that you have to run to start the container, start the application. This is what is then going on. Okay. It's usual cases, it's just to run your application. Okay. So this specifies the command to run the Docker image either run as a container. For example, cd python app.py, specify the app.py should be run using Python interpreter when the Docker image is run as a container. Okay. Then expose. So we need to see this windshield, right? See what's coming, what's going on, this interaction happening, or where to drive and all that. So this exports commands kind of that. It's open a port, a window glass, where the Docker will be able to communicate. Like say anyone want to say something, show the sign, want to see what's coming. Say we're running a car, we see the sign and all, right? So it's getting the input from the windshield. So this exposing, we're exposing a port where it's allowing the traffic to come. So any request coming, it should come to that particular port, right? So that expose part happening. So expose is exposing a port for use by the container. For example, expose port 80 for if it's the HTTP application, expose port 443 if it's a HTTP application to allow HTTPS traffic, right? All those things. Now env. So env is a, if you want to set some certain environment variable, then you should go and use this env command. Okay. Now to build an image, you should run docker build, then -t. Then this t means tagging. You are tagging a particular name, my image name, and then dot. So see, there's a space between your image name and dot. Dot means current directory. If you do two dot means previous directory. If you didn't particular one path, that means Docker will use that path at their base directory to copy the files and do it. Okay. And but you have to remember, wherever this path, dot or slash, whatever is your path you're giving, that must contain a Docker file. This is where Docker build going to look for the Docker file. Okay. After your Docker, you make the image, you can run the image by running Docker run, then the image name. So my image name is my image name, for example. You can simply run like that. And here is a pretty basic example of a Docker file to run a flush cap. So if you want to create a Docker file, of course, you need a file called Docker file. Let me quickly show code. And code say new. Where is new window? Yeah, new window. Okay. So if you see here, let's open our Python folder that I had. So Python cloud. See, this code I have shared long time. It's already available to everyone, I guess. See, there is a Docker image should be there, I think. Docker should be episode 3. Flush cap. Yeah, there's a Docker file. See this Docker file there. So it's using Python 3.8 that time when I was making this series. So ultimately what it's doing from base image. So Python 3.0 is actually available. If you go to Docker registry, say Python. See Python official image of Docker, right? And there is a path, like see this one, all the stacks are there, right? But this is ultimate path, Python, right? So Python, so it's this Python is actually referencing to this default Docker hub by this Python. Okay, this Python means this page, okay, or this some kind of virtual repo. Now, the moment it's not saying anything, it will simply install. See, we're saying the slim buster, right? Slim buster, meaning smaller image, only the things we need. So that is, see, the slim buster all should be there. Okay. So, see slim buster and all that. So it's a tag, slim tag. Similarly to the slim, it should be slim buster and all that. So it's simple tags. You see all the layers and everything in this particular thing, very useful. And you want Linux, you say AMD 64 or any particular architecture, you can go for that. Advanced stuff, I know that's going to cover in the next week. Not going to complicate you guys. So simply it's a tag name. Ultimate, this is a repo which have all the tags. Then it's have the slim buster. What is that? This 3.8 slim buster. Let's look for that. Should be somewhere, okay. Yeah, see slim buster 3.12 also is now there, right? So you see the images, right? See slim buster and all that. You can see Python, then this colon, then the tag name, right? That's, we are just using one such tag. So every tag in this is what? They have lot of Docker images. Out of, like, how to identify the Docker images? If you have 10 Docker images or any container images, we need to identify somehow, right? So this is how we identify, say versioning. So for Python, we want the image, whichever Python 3.8 version, and you want a still slim version. So you'll simply go to Python, container registry, then you want to look at this 3.8 version. That's it. So this is how we can get from the Python. Okay. And after getting the base image, in the base image, it's already have the Python. So we don't, I mean, this operating system, this Python image already have the operating system, already have the environment set to run Python. So you don't have to install Python anymore. We are dealing with the working directory. So we are creating a work directory app. There we are first copying the requirements. So what do we have the requirements? The modules, right? Click, Flask, Jinja, and all these things that we need to run the application. So in Dockerfile, we have all these requirements, right? So sorry, we are copying our local this requirement.txt into the container. So while running the build will create a temporary workspace or temporary folder. In that temporary folder, it will copy this requirement.txt and it will install all the required, see, all the modules that you have mentioned here as per the requirements. It will install in that temporary workspace or temporary directory. Okay. Then what will do? Then it will install by running this pip3 command only, is installing all the stuff. Then it's copying entire stuff that you have in this particular folder. So in our Flask app example, whatever content we have, there should be, of course, a Docker ignore. I think I missed the Docker ignore, but we should not copy the VMware file. But it's okay. It will not do any effect. It will just take us extra space or something like that. But ultimately, what this copy dot is doing, this dot means the directory that you do that have this Docker file. Okay. So dot in this is entire directory you copy to this dot, means this app directory. This is the workspace, right? So the moment you are mentioning the workspace, that means current work directory is moved to that workspace. So current work directory is /app right now. Okay. Now there it's inside this app folder is copying entire this Docker file, index file, everything, whatever the code you have, it will copy there. And then in order to run application, what you have to run? We have to run Python, then -m, there's a module Flask, then run. Then what it will do? It will simply look for this app.py, sorry, index.py, and it will run that one. It's automatically, right? So this is a very pretty easy example. Now, similar we can do for the Django also. I think Django we don't have here, but we have in our demo. So let's go with our demo. Demo part, just already know, maybe you want to run by yourself. I will just quickly show, by the way. So I will go to the terminal and it'll show you how to run the builds. So new terminal, then let's go to the cd ep2, then cd Flask example. Then you run docker build -t. T means tag. We're giving a name to the build. My simple demo. Then we have to give space. No, it's a space. You have to give the tag version 1, for example. Then dot. So this dot means I'm in this particular Flask app example directory, and this current directory have this Docker file. Otherwise, it will give you error. If you run it, see, start making the build. First is loaded, see, load and transferring on all this. You can see it's already moved. I cannot show anyway, but later on, see, it's run it's already have the image. So now if you do Docker images, yeah, I have all the image. It should be my simple demo and tag is version. So this is a repository name, my simple demo, and the tag name is actually the v1 tag that I've given. Okay. So this command, this one is my repo name, and v1 is the tag name. Okay. So this is how we can make Docker image, and if you want to run, you can run Docker run, then this particular image, and it will run. Okay, like simple how we are running normally. Yeah. So this is the instruction for the Flask app if you're running the latest version. simply from Python 3.9 Slimbuster. You know how, where from we're getting this particular image. Then working directory, we're setting the working directory. We're copying the requirement from the local to the container workspace. Then we're running npip install, installing all the system in this particular pre-installed Debian OS, because this Python 3.9 actually a Debian-based OS which already have Python installed. Then we are running pip install to install the requirements. We are copying entire directory, all the codes to this particular app folder. Then you're exposing 5,000 because that's where default is running. Then you are exporting, we're setting environment variable. So Flask underscore app is equal to app.py. Now Flask knows what is my actual app. It's not index, right? So it's app.py. So we need to specify it. So it will simply go and look for app.py. And if you see the Flask, then run. The command is Flask run host, because it's already the moment you are installing requirement. Inside the requirement, we have the Flask. So Flask is installed, so you have it. We can just use Flask run, then the host where you are running, it will run the Flask app. Similar thing you can do for the Django. So it's same base image 3.9 Slimbuster, work directory setting. We are copying the requirements, installing the requirements, copying all the code from locally, then exposing port 8000. Then we are setting environment setting module, my procedure setting, if you have any. Then CMD, we are running this first run migration when running containers. If you have some migration, say DB migration or something like that, you run Python manage by migrate, and then you have start the Django development server. So CMD, Python, then manage Py, then run server where you want to run the server, right? So this is how you can do the Django. Now you want to, containerize any generic Python app, okay? Like not Flask, not Django. This is a very generic application. So again, Python from base image, Python 3.9 Slimbuster, work directory / app, you're setting the default directory. Then you're copying the requirement, the txt, then you're running pip install and all the requirements you're installing. Copy, you're copying all the files from local directory, local codes to the this app folder, then exposing port 8000. It's 8000 here. You can expose any port you need. If you don't need any port, don't expose it. Easy. Then you're running Python, then app. Any app you're going to run, you can run it. So this is how easily you can run a Python application. Okay. I think next week we're going to cover the advanced Docker and containerization. Good day.